Thanks for joining us for Phosphorus Science Now. I'm Matt Schultz with the Sustainable Phosphorus Alliance. Precision nutrient management is a high-tech way of applying nutrients to crops in a more targeted fashion than traditional fertilization methods. It holds the promise of optimizing nutrient applications for better agronomic, environmental, and economic outcomes by treating each subplot of a field with its own quantities of fertilizer, rather than simply applying the same amount of fertilizer across the entire field. Today's speaker, Dr. Vaugh of Mississippi State University, was part of a team that investigated whether our standard method of using soil tests to determine optimal phosphorus applications at the field scale also works at the smaller scales targeted by precision agriculture. Spoiler alert, it does not. Well, thanks, Vaugh, for joining us for Phosphorus Science Now. This was a really great paper, and I'm excited to have you on the show.
Thanks for the opportunity coming on. So this manuscript that we finally got published in January was a long time coming. We looked at soil test phosphorus and would it be able to predict field level but not sub-field level corn yield response. This study was started in about 2015, and from 2015 we had many collaborators on until finally getting this published roughly about 10 years later. So as you can see, we had a large team of 9 authors attached to this. Mr. Jimmy Bowen had started this. He was a PhD student at the University of Kentucky when this project started. Unfortunately, he passed before we were able to get this out and published. So then when I got hired on as a postdoc in 22, I picked this up, and between me and the other collaborators, we finally got this pushed out. This was funded and supported by the USDA NRCS in their Conservation's Efforts Assessment Project, and then also supplemented support with IPNI, formerly known as IPNI, as the International Plant Nutrition Institute.
Great, thanks. Yeah, go ahead and launch into it.
So our current fertilizer recommendations, depending on most land-grant universities or institutions across the U.S., their fertilizer recommendations are going to be based upon a correlation calibration study where a soil test result is going to be correlated with a yield response. So in this case, below a certain soil test value, we're not hitting 100% yield. And then you would expect above this value, then you're finally getting a positive yield response, or you're finally actually maximizing your yield. And so we don't need to apply any fertilizer above this line. So this is the way most universities have been over the past, 50, 60 years. And in order to implement these studies, these land grant institutions would go out, put all of their studies at a bunch of their different research stations across their state, bring the data back, and then try and make a fertilizer recommendation that worked averaged across their state. So I work at Mississippi State University, so I'm now responsible for most of the state of Mississippi. Just looking at a map, you can see the variability of different soil types and the variability of crops grown in the region. If we pull up a soil map, you can see the predominant delta part of our state, which has neutral acidic soils, lots of sands and clays with a lot of irrigation. And those same fertilizer recommendations have to work on the other side of the state, which is just completely different from one another. But all these land grants would put together their correlation calibration, make a fertilizer recommendation, and try and make them work on average. So this is a fake data set trying to make this really pretty line, really good correlation. What we want to see is a nice clean line like this, but in reality, what we end up seeing is a lot of noise everywhere. Nothing is working perfectly every time, but you add enough points together and then you start putting together some sort of model to say, how much fertilizer do we need and where do we need to put it? And this isn't just an issue of the amount of data collected, it's the type of data collected. Here's a collection of over 15 states in the continental US, their phosphorus fertilizer recommendations all compiled together on a correlation figure, and it's just as unclean and just as noisy as one state's data. So our objective was to evaluate the effectiveness of just using a soil test value to predict crop nutrient response at a subfield level as you would try and use to support variable rate fertilizer technology. We also wanted to examine some of the spatial variability and soil test critical levels within fields to get a better understanding of what we're seeing across different locations. So we had two locations established in Kentucky, one on the eastern side of the state, one on the western side of the state. Both of these are fairly representative of the region, of the row crop production in the area. And instead of taking multiple fields, larger fields, and trying to get one data point from each one of those fields, we took two rather small fields, 12 acres for one, 6 acres for the other, and split these up into multiple research plots. And so each square that you're seeing here represents one main plot, or basically one response plot. Each main plot was split with or without getting phosphorus fertilizer application to a soil testing density of about 2/100ths of an acre. So each one of these plots were extremely small. And we had paired plots across the entire field. And so each one of these square main plots would give us an indication of, in that area, how well did the phosphorus fertilizer do? Did we get a positive yield response? Did we just not get any yield bump from the application?
And Vaughn, if I
And
can interrupt for just a second,
sure.
when you talk about a 0.02 acre plot, how's that compared to what's typically done for soil testing?
For soil testing across most of the US, 2.5 acre grid is fairly representative, maybe up to 5 acres in some regions, maybe down to 1 acre grid. But we are several magnitudes more dense
Yeah,
than most other production standards.
great, thanks.
Yeah, we had a significant amount of data associated with this. If we looked at the soil test phosphorus values, so University of Kentucky utilizes Mehlich 3 extractable phosphorus. You see on this figure here, or both of these figures, you'll see a dotted vertical line. This just represents the cutoff value for the University of Kentucky, which is 30 parts per million or 30 milligrams per kilogram of Mehlich 3 phosphorus. Anything below that, we would have we would have made a phosphorus fertilizer recommendation to. Any above that, we wouldn't. Across both of these locations, and we had 3 years of data collected in Princeton at the Western Kentucky location, 4 years of data collected at Quicksand. We can see that 91% of all the main plots together were below at both locations, were below our recommended cutoff value. Therefore, we would have made a large fertilizer recommendation across all of it. So if we wanted to evaluate just how accurate our fertilizer recommendations were, across all 4 years, we had very low soil test value. We would have made a fertilizer recommendation across all 4 of these years. And yield with fertilizer and without fertilizer, we saw a yield increase by just applying some phosphorus fertilizer. So this tells us that our fertilizer recommendations, on average, are accurate. We had low soil test values, we applied it, we got a yield bump. The problem was, and what happened is it fell apart when we were trying to look at the precision of our recommendations. So what we really want is a really nice and clean curve that provides us a clean correlation of soil test values to a yield response. And unfortunately, what we get looks like this. A lot of noise everywhere, never really converging on a good soil test value or a high relative yield. And even our critical value, where this joint is and all of these figures, is where above that line we would not make any application of fertilizer. Below that line, we would have made a significant fertilizer application. We're looking at about 10 to 20 parts per million, even lower than what the current University of Kentucky fertilizer recommendations stand at. Most of the time, the anecdotal evidence that we hear is that our university recommendations are actually fairly low, and we need to bump that up. But according to the data collected just over 2 different locations, multiple site years, but 2 different locations, said that our soil test values were actually, or the critical point value is actually a little low, or as high. We're at 30 parts per million, even though all of these models kind of converge around that 10, 20 parts per million area. So that's the main takeaway from this manuscript, this publication, was that our fertilizer recommendations alone are not able to truly predict yield response. Since then, we've kind of gone back and tried to look at what are some of the other components that are impacting yield. We've collected Malic 3 using principal component analysis. At Eastern Kentucky, it looks like Malic 3 phosphorus and soil pH, two of the predicting values that you would normally get out of a soil test, do a pretty good job at looking at soil test values and correlating that to a yield response. But if we look at the other location and Princeton, soil test values had almost nothing to do with the yield response. And we had extremely high variance across all three of these locations. Some of the other stuff we're wanting to look at going forward is using more principal component analysis, but also trying to use other soil test values that you don't normally get out of a soil test, which would be like organic matter. Trying to correlate to, does an increase in yield sometimes correlate with an increase of organic matter? Therefore, some other nutrients might have be better available for that region. Our key takeaways from this manuscript is that current recommendations work on average, but lack the precision required to fully support variable rate application. I am a nutrient management researcher. I focus a lot on this. I am a big proponent of variable rate application is going to get us where we need to go, limiting our waste on fertilizer application. But currently, we're using it without all the data required to really back it up and provide all the defense and support you need for it. We must start looking into other variables that might be available. This could be downforce, this could be penetration values, this could be the slope. We could use some DEM models to, provide us a little more information about each one of the fields. We have to look a little bit deeper. The most important thing that we came out with this publication with, it was not necessarily focused on the producers and stakeholders, but on the researchers themselves. And we're talking to us. Researchers must start trying some different approaches to make better recommendations. The problem isn't that we aren't collecting enough data. The problem is that we're collecting too much of the data that made the previous fertilizer recommendations, not that are actually going to build up for our future fertilizer recommendations.
Great, thanks a lot for that, Vaughn. So one question I have, I guess, is that if a farmer wants to do, precision phosphorus on their fields, is the state of the art such that we just can't support them right now?
I don't know that we can't. If a producer's wanting to use some sort of precision ag, variable rate technology and base that on to a certain basis, our recommendations are going to get them 90, no, I don't want to say it that percent. They're going to get you a significant way there at getting you an on average recommendation. The problem becomes, and this is something that I live with, getting phone calls on, weekly basis of my soil test says that I have this value, but I applied fertilizer anyway, and I still saw a yield bump. That means your all's recommendations are not working as they should. We just got to get a little bit closer to really pinpoint the areas where we do need it and pinpoint other areas where we don't. We have the data to back up that it'll work on average. It's just not going to work every time.
Gotcha. Okay. Thanks so much for that clarification. And again, really thank you for this paper. It's a great paper. I recommend people read it and get into the weeds if they're interested. And thanks again for joining us.
Yeah, I appreciate the invite and thank you for highlighting this work. It took all of us and we're really proud of it.
You should be. Thanks.